Okay, at the end of the last video, we were looking at finding stationary point and establishing and determining the nature of these stationary points. We had worked a problem. I summarized it back right there. The equation was y is equal to 3x to the fourth minus ax cubed minus 8x cubed plus 6x squared minus 3. First derivative was shown there. We had found that there were two stationary points. I'm not going to go through the details again. You can go back to the previous video to check. We found that there were two stationary points, and one of the stationary points at 0 minus 3, the second derivative test was able to tell us that that stationary point was minimum. However, for the second stationary point at 1 minus 2, second derivative test failed. It could not tell us what type of stationary point we had. So in this video, what I'm going to do, I'm going to use the sign test on the first derivative that will allow us to establish the nature of the stationary point. And we're going to use the same example. So it says here, I already have this information summarized. When the second derivative test fails, the sign test on the first derivative can be used to determine the nature of the stationary point. Okay, let's see how. Let's say we have the x value of the stationary point as shown in this little diagram here. That's the x coordinate of the stationary point. What we're going to do, we're going to choose two values of x. And it's totally up to you. You're going to choose two values of x, one of them on either side of the stationary point, but close to the stationary point. There it says, choose two values of x, one on either side of the stationary point, but close to it. And then we're going to calculate the value of dy dx at each of these points. We already know the value of dy dx at the stationary point is 0, because by definition, at a stationary point, dy dx is equal to 0. So we don't have to plug the x value back into dy dx at the stationary point itself, because we already know that that's 0. And basically, here is the summary. You're looking for how the sign, SIGN, how the sign of dy dx changes as you go through the stationary point, from just before it to the stationary point itself, and then just after it. In the first scenario right there, it says if dy dx is greater than 0 just at x1, which is the point, which is the x coordinate just before the stationary point. If at x1 dy dx is greater than 0, that means, I'll do this over. At x1 dy dx is greater than 0, that means you have a positive slope. At the stationary point itself at x, dy dx is 0, which means you have 0 slope. And then just after the stationary point, you have dy dx is less than 0, which means you have a negative slope. That clearly means you're going through a maximum stationary point there. Stationary point is maximum. Vice versa, if at x1, the point just before the stationary point, dy dx is less than 0, which means you have a negative slope. At x itself, the stationary point, we already know the slope is 0, the gradient is 0. And at x2, just after the stationary point, the gradient goes positive. Then you know you're going through a minimum stationary point. And then if the gradient or if dy dx changes from positive to 0 to positive here, or negative to 0 to negative here, then you know in either case you're going through a point of inflection. So we're going to check. We're going to go back to that same problem, summarize the information that we need, and we're going to determine the nature of the stationary point. So let's see. The equation of the curve was y is equal to 3x to the fourth minus 8x cubed plus 6x squared minus 3. The first derivative, dy dx, was 12x cubed minus 8 3 is 24. Minus 24x squared plus 12x. That's the gradient function. Any value of x we plug into that gradient function, we get the gradient at that point. Now you remember we already have the stationary point that I'm interested in. The coordinates of that stationary point were 1 and minus 2. Stationary point, 1 and minus 2. And the second derivative test was unable to tell us what type of stationary point it is. So we're going to use the sign test on the first derivative. I'm going to pick the two values on either side of the stationary point. The x coordinate of the stationary point is 1. So I'm going to do it just a little bit before x equals 1. Let's say x equals 0.9. Then x equals 1, which is the x coordinate of the stationary point itself. And then to the right of that, x equals 1.1. And I'm going to plug those values of x into dy dx. So when x is equal to 0.9, dy dx is equal to 12 times 0.9 all cubed minus 24 times 0.9 squared plus 12 times 0.9. And that value ended up being a positive 0.108. We know at x equal 1, I don't have to plug that value into dy dx, because I know when x is equal to 1, I have a stationary point. So dy dx is 0 when x is 1. And then just after the stationary point itself, when x is equal to 1.1, dy dx is equal to 12 times 1.1 all cubed minus 24 times 1.1 all squared plus 12 times 1.1. I crunched that value also before, and I got positive 0.132. 0.132, a positive number there. Now, here's what I'm looking for. I'm looking for this number, which represents the gradient of the curve just before I get to the stationary point, the gradient of the curve at the stationary point, and the gradient of the curve just after the stationary point. And what do I notice? That gradient went from a positive gradient like that to 0 gradient at the stationary point itself and back to a positive gradient. So clearly, I'm going through a point of inflection when I do that. Right? So therefore, the stationary point with coordinates 1 and minus 2 is a point of inflection. What you can do for me is to go back and, I'll eventually get this thing. Yes, is to go back to the other stationary point on the same curve. Remember, we already know from the second derivative test that 0 minus 3 was a minimum point. Check. 0 minus 3, which we already know from the second derivative test, is a minimum. Check using the sign test on the first derivative. So the x value, I'm just suggesting, you can use just before x equals 0 would be x equal minus 0.1. And of course, x is equal to 0 itself at the stationary point, and then x is equal to a positive 0.1. Plug those three values into the dy dx function, into the gradient function, and confirm that this test will also tell you that this is a minimum stationary point. And then I've given you a worksheet here on all types of stationary points. whether it's minimum, maximum, or otherwise. From your advanced text, exercise 10.12, page 436, number 7, 8, 11, and 15. That should give you a good workout. By the way, I made a comment in the previous video that the sign test on the first derivative might not be so applicable to the ADMAT syllabus. Well, it is. So ignore that comment. That's why I went through this in full. All right, that's the end of this video, and I'm coming back with more. The next video I'm going to do is probably going to take you to cases where you have to now learn other rules for differentiation, not just the one single rule for differentiating a polynomial. So in subsequent videos, you're going to see me go through those. All right, that's it for this one. Take care.